Now we will continue with the other methods for the determination of equivalent single V load. So the references are Payment Analysis and Design by Huang and also the Principles of Payment Design by Yoder and Witzak. So the other four approaches, we have already seen the equal vertical stress criteria by Boyd and Foster and Alvin. And then now we are going to discuss the approach by equal vertical deflection criteria, then equal tensile strain criteria, and then the criteria wherein an equal contact pressure or an equivalent contact radius is considered. So this is the third approach, which is the equal vertical deflection criteria to get the equivalent single V load. The application of the earlier methods or the Boyd and Foster's method and subsequent completion of accelerated traffic test, it is found that the design is found to be less safe. The Foster and Alvin suggested an improved method wherein the payment is considered as a homogeneous half space and the vertical deflection at a depth is equal to the payment thickness is found from the Bosnick solutions. And equivalent single V load is considered as that single V load which has the same contact radius A as that of the dual wheels and which will result in the maximum deflection equal to that caused by the dual wheels. So here the maximum deflection at the bottom of the payment layer is considered as the criteria for finding the equivalent single V load. This is a chart again you are familiar with. So this is the vertical deflection factor F for different depth as per Foster and Alvin. This is taken from Huang. So you can get the vertical deflection factor for the single wheel as well as the dual wheel, and from which the vertical deflections can be estimated and the vertical deflection can be, or the deflection expression for vertical deflection can be equated to find the equivalent single V load. Now as in the case of the equal vertical stress criteria, here also if you have the dual wheel, so this is a dual wheel, in the case of the dual wheel, there could be three possible points where you can have the maximum vertical deflection, which is point number 1, which is exactly at the middle of one wheel load, or it could be point number 3, which is midway between the two wheel loads, or point number 2, which is midway between 1 and 3. So you have to see where you get the maximum deflection factor at the points 1, 2 and 3, and the effect of two loads has to be superposed together, that is the left wheel and the right wheel has to be superposed together to get the deflection factor at these 3 points, and then find the maximum of this in the case of a dual wheel. Okay, and this has to be equated to that of a single wheel so that you can arrive at the equivalent single wheel load. So let's see how we are equating these two values. So as you can see here from the chart, you get the deflection factor F for different depths or Z by A values, and each of these curve indicates or is for a different R by A value. For R by A from 0 to 8 you have different charts, and once you get the deflection factor F, you multiply it with QA by E in order to find the vertical deflection, okay, due to a circular loading of radius A and a contact pressure of Q and in a payment of modulus E. So equating the vertical deflection or finding the vertical deflection due to a single wheel, that will be QSA by E into Fs, that is the deflection factor due to the single wheel load. And in the case of a dual wheel, the deflection is given by WD is equal to QD A by E into FD, where FD is the deflection factor for a dual wheel assembly. So here A, the radius of contact of the dual wheel and the single wheel is kept same, as well as the payment modulus is the same, whereas the pressure indicated or the pressure imposed by the single wheel and the dual wheel is different, which is denoted as QS and QD. Okay. Now equating this maximum deflection as Ws is equal to Wd, that is the deflections are equated, you can note that QSFS is equal to QDFD. Now as the contact radius is the same, so your QS is actually proportional to the load, which is P. So you can get PS is equal to FD by Fs into PD. So from here we note that FD is the deflection factor for the dual wheel assembly, the maximum deflection factor for the dual wheel assembly, Fs is the deflection factor for the single wheel, and PD is one of the dual wheel loads. So, multiplying with this ratio, you get the equivalent single wheel load. So, let us attempt the same question which we have discussed for the past two methods using this Foster and Alvan's method of equal vertical deflection criteria. So, a set of dual tires having a total load of 9,000 pound and a contact radius of 4.5 inch and a center to center spacing of 13.5 inches given here. Again, it is a homogeneous half space with E1 is equal to E2. You are asked to find the equivalent single axle load for this dual wheel assembly based on the Foster and Alvan's method. So, let us see how we do it with the Foster and Alvan chart. So, first of all, for the dual wheel assembly, a table is drawn here, written here with the left wheel. So, this is the left wheel and this is the right wheel. So, the approach is exactly same as what we have done for the previous one with sigma Z. So, a similar approach is here. So, you have a left wheel and a right wheel, and you have to consider 2 points, 3 points in the case of a dual wheel. So, this is point number 1, and midway between the two, this is point number 2, and midway between that, this is point number 2 and this is point number 3, which is marked here as 1, 2 and 3. And first let us see whether it is only when there is only a single wheel load. So, when the single wheel load, the point is this 1 itself where you will get the maximum deflection, and R by A value for that point is 0, and Z by A is, as in the earlier case, it is 13.5 by 4.5, which is 3. So, for an R by A of 0 and Z by A of 3, you can note the F value from this chart. Okay. So, F value is directly read. So, we see, let us see, this is R by A of 0 plot and Z by A of 3. So, it will come somewhere around here. So, this may be close to 0.48 as I said. So, this could be somewhere around 0.48, but since this is noted from computer analysis or using Kendler software, that is why it is written as 0.478. You can note what is noted, whatever you note from this chart. So, 0.48 or 0.478 is the deflection factor. Similarly, so this is the case of a single wheel load. Okay. Now, you have the dual wheel load. For the dual wheel load, let us see, the left wheel value is the same. Now, the right wheel value for an R by A value of for the point 1, the R by A value is 3, as we have already discussed. That is, the distance from the load point to the point number 1 is R divided by A will give you 3, okay, because it is 13.5 by 4.5. So, for that R by A value, you get the Fs value. Similarly, consider point 2. For the left value, you see what is R by A, which is 0.75. You read the F value from the chart, which is 0.443. Again, you may get it as 0.44 only. So, since this is noted in Huang from the computer analysis, so that's why I have taken the same chart here. So, this is 0.443. I'm sorry. You may get it as 0.44 from when you read from the charts, but since this is computed using Kendler or so. Okay, so for the second point here, you can note that for the left wheel, the R by A is 0.75 and the right wheel, the R by A is 2.25, and you can read the corresponding F values from the chart. So, you may read it as say 0.44, 0.32, etc. But since this is done using a computer program, that is why they have arrived at this values of 0.443 and 318 and so on. So, this is taken from the Huang textbook. So, I have used the same tabular form table from the Huang textbook. So, you can read as what you see here. Suppose it is 0.44, you can write it as 0.44 itself. Okay. So, you got the values at the point 2. Likewise, you can consider the point 3. You get the values for the left wheel and the right wheel, and the left wheel and the right wheel coefficients or the deflection factors are to be summed up to get the total deflection factor FD for the dual wheel. So you see that at point number 1 your value is 0.741. Point number 2 has a FD of 0.761 and the point number 3 has a value of 0.78, of which the maximum value is 0.78. Now the equivalent single wheel load is given by any one of the load, which is the PD, multiplied by the dual deflection factor divided by the single deflection factor. So single load deflection factor. So it is 0.78 divided by 0.478 into 4500. So you read that 7340 is the equivalent single wheel load based on this approach. It was the same question that we have discussed for the other approaches as well. So you see that this closely matches with the approach that we have discussed earlier. Okay. Now, the Foster and Alvin method that we discussed just now has considered a homogeneous half space, that is the payment has only one layer, which is not logical because your subgrade and the payment layer, we may have multiple layers. So at least 2 layers are to be considered because you are subgrade and you have a top payment layer. Okay, so the layers but the approach has the design based on that approach was also giving a more or less okay design, or the layer thicknesses were found to be so the approach that we have just discussed based on Foster and Alvin for using vertical deflection have considered that the payment is a homogeneous half space, that is it comprises of just one layer having a modulus of E, which is not logical because the payment structure should have at least one layer which is the payment structure and at least 2 layers which is the payment structure and the subgrade layers. Okay, but and also it was found that the layer thicknesses which were designed based on that approach was inadequate. So Huang has considered the layer theory to find the equivalent single wheel load based on interface deflection of 2-layer system. So you consider a 2-layer system with E1 is the top layer and E2 is the bottom layer, and the vertical deflection at the interface of these 2 layers is considered for finding the equivalent single wheel load. Okay. Now to get this, you can use a load factor is considered from a chart which is depending on various factors such as the contact radius, the thickness of the payment, the E1 by E2, the modular ratio and the spacing between the dual wheels. Okay. And then the load factor is given by the total load divided by the single wheel load, equivalent single wheel load, or the equivalent single wheel load can be denoted as twice the total dual wheel load divided by the load factor. Okay. Now, from the Foster and Alvin equation, we know that equivalent single wheel load is the deflection factor for dual divided by the deflection factor for single into PD. Now, comparing these two approaches, we see that the load factor can be written as twice the Fs deflection factor due to single wheel divided by the deflection factor due to the dual wheel. Now, for this expression, which is L is equal to 2Fs by Fd, either you can use the same charts to find the deflection factors and then use this, but this may be very cumbersome. So what is done is that for this expression, there is a chart which has been derived or a chart that has been developed. So this chart is given as figure 6.4 in Huang. So you see that this chart is for different E1 by E2 values with 2 different contact radius. The first one is for a contact radius of 16 inch and the top one here is for a contact radius of 6 inch, both drawn for a spacing of 48 inch. Now, instead of using this, so this is a chart that is developed to find the load factor, or instead of using this, you can use the deflection, vertical interface deflection for 2-layered systems given by Huang can be used. For example, the figures 2.19 in the Huang textbook, where there are 7 plots which are given for each one for a particular E1 by E2 value. For example, I have shown some of them here. This is the vertical interface deflection for a 2-layer system with an E1 by E2 of 1. and this is the vertical interface deflection values for an event by E2 of 2.25. This chart is for an event by E2 of 5 and so on. So either you can use these charts to find the deflection factors, or this combined chart which is used to get this load factor. You can use this load factor approach. This will be a simpler approach to use this chart given in figure 6.4. Okay. So the procedure is like this. As you can see here, this is for a SD. So here it is noted as S. So SD is for 48 inch. The dual wheel spacing of 48 inch, this chart is developed for that. So, and also for the contact radius of A is equal to 6 inch or A is equal to 16 inch. So accordingly they are denoted as L1 and L2 are the two load factors. But suppose in the question you have a contact radius which is different from 6 inch or 16 inch, or you have a spacing of other than 48 inch. In that case you have to find you have to get a modified radius and a modified thickness as given here, where A dash is equal to 48 by SD into A, and H1 dash, that is an equivalent pavement thickness, which is 48 by SD into H1, which is the thickness of the original pavement. The idea is like this. So if your question is with a different SD value and a different contact radius, you have to find a modified radius as A dash is equal to 48 by SD into A, and a modified pavement thickness which is H1 dash is equal to 48 by SD into H1. So what you are trying to do is that this ratio of the spacing of the dual wheel and the pavement thickness is to be kept constant, so that you can find a equivalent thickness, so that the charts which is provided for 48 inch spacing can be utilized. Okay. So that is the whole idea of finding a new A dash and an H1 dash. So use this H1 dash to read the load factors from the chart that is shown earlier. Okay. So you can get the load factors from L1 and L2 if your contact radius are not 6 and 16 inch. Then what you have to do is that you have to interpolate the load factor for the given contact radius, which is L1 minus 0.1 into A dash minus 6 into L1 minus L2. Once you get this load factor, then 2 PD by the load factor will give you the equivalent single wheel load. Let us work out the same problem again with this concept and see what will be the equivalent single wheel load. So, as already discussed, this is 4,500 pound and 4,500, a total of 9,000 pounds with a spacing of SD spacing of 13.5 inch, and you are asked to find the equivalent single wheel load when the pavement thickness is Z is equal to 13.5 inch. And in this case, this is a two-layer system, and one is with E1 by E2 value of 25. So E1 is the modulus of the layer 1. So this is the top layer or the pavement layer, and this is the subgrade layer. So this is layer 2. So E1 by E2 ratio is 25, and at the same time you are also asked to check whether if it is a homogeneous half space, that E1 by E2 is equal to 1. So let's use this approach. So first of all, what we have seen is that SD is not equal to 48. So you can't directly read from this chart. So what you have to do is that you have to get A dash, which is given by 48 by SD into A, where A is the contact radius. So it's 48 by SD given as 13.5 into A, which is 4.5, you get it as 16 inch. Okay. And you have to find a new thickness, which is H1 dash, which is 48 by SD into H1, you get it as 48 inch. Now let's see the chart. You see that first of all, let's see that E1 by E2 is equal to 25. Okay. So when we look at the chart, you see that this chart is for A is equal to 16 inch. So you can directly read from chart, the bottom chart. You don't have to take the top chart and average or find interpolate and find it. So for H1 dash is 48 inch. So from here, so this is 40, this is 45, 48 inch, somewhere here is 48 inch. So for E1 by E2 of 25, you can read from here, you see that your somewhere close to 1.05 or 1.06. Okay, so the L value is read from the bottom chart because it is for A is equal to 16 inch. So your A dash here is 16 inch. So you got it as 1.06. Now 2 PD by 1.06 will give you 8,490 pounds as the equivalent single wheel load. Okay, so this is for a payment structure with E1 by E2 is equal to 25. Now this is the first case where it is mentioned that E1 by E2 is equal to 1. So again you can read from the bottom chart, you see that this is E1 by E2 is equal to 1. So when you read it, you see that L is equal to 1.22. So if you find the equivalent single wheel load for a homogeneous half space, you got it as 7,377 pounds. So this is similar to the deflection of the homogeneous half space that you have already determined, which was close to 7,400. Okay, so whether you use this chart or the homogeneous half space deflection criteria, you will get the similar answer. So the idea here is to consider the layered system with different E values for the payment and the subgrade. Okay. Now moving on to the next criteria. So we have already discussed the criteria based on the vertical stress, then based on the deflection. Now the third one is you are going to consider the tensile strain at the bottom of the payment or the bottom of the payment layer. So you have already discussed how to determine the tensile strain at the bottom of the payment layer or the bituminous layer. Wherein you have a chart available for finding the tensile strain for a single wheel, and then there are conversion factors if there is a dual wheel or a dual tandem wheel. Okay, so the tensile strain at the bottom. So this was the chart for from Huang, figure 2.21. So the tensile strain for a single wheel load application is given by E is equal to Q by E1 into Fe, where Fe is the strain factor that can be read from this. And if your load has dual wheels or dual tandem wheels, there were conversion factors given so that the strain can be noted from this chart to find you get the strain and multiplied with the conversion factor to get the strains corresponding to a dual well. So this is how the tensile strain was computed from the charts. So you see here is the conversion factor for the dual wheel, which was given in Huang in 2.23 figure. So these are the conversion factors for SD spacing of 24 inch for two contact radius, one is for 3 inch and the other is for 8 inch, and if you get a different contact radius, you have to interpolate from this. So this is already discussed by Professor Murli in his analysis of systems lecture. And this were the conversion factors for a dual tandem assembly. So this was a dual tandem conversion factor for a dual tandem assembly with a spacing of 24 inch. So this is the tandem spacing of 24 inch and the dual wheel spacing of 24 inch and a contact radius of 3 inch. And the bottom one is for a contact radius of 8 inch. And the second conversion diagram was for a dual tandem wheel with 48 inch tandem spacing, and the third one was with conversion factor with a tandem spacing of 72 inch. So this were the conversion factors to find the tensile strain when you have a dual tandem wheels. Okay, so as I mentioned, the single wheel, the strain is computed as E is equal to Qs by E1 into the strain factor Fe, and for dual or a tandem wheels, you find the conversion factor C from the chart and multiply it with the other factor to get the tensile strain. Okay, now equating, so these are the two expressions to find the tensile strain due to a single wheel and a dual wheel. So the same approach can be used to find the equivalent single wheel load. So equating this these two expression or the strains, we see that Qs, that is the pressure, the contact pressure in the single wheel is equal to C times the contact pressure in the dual wheel. And since we are considering equal contact radius, your contact pressure is proportional to the load. So you can say that your PS is equal to C times PD, or PS is actually your equivalent single wheel load. So let us work out one example. to find the equivalent single wheel load based on this equal tensile strain criteria. But it is a similar question what we have been discussing, but only thing is that the pavement thickness is changed to 8 inch than 13.5 inch. Okay. And the E1 by E2 ratio is given as 50 here. So what you are going to see is what is the epsilon T or the tensile strain at the bottom of this pavement layer, and for the dual wheel, and this strain is equated for the dual wheel assembly and to the equivalent single wheel load. Okay, so first of all, let's see what is the spacing given. So 13.5 is the spacing, but since the spacing that is given in the strain computation is 24 inch, you have to convert it to, you have to find the A dash and H1 dash. So this is already explained in the tensile strain computations. Okay, so you get A dash as 24 by SD into A, which is 24 by 13.5 into A, which is 8 inch, and H1 dash is 24 by SD into H1, which is 14.4 inch, 14.2 inch. Now A dash, this conversion factors given for a dual wheel is for a contact radius of 8 inch and for a contact radius of 3 inch. Okay, so in this case you got the A dash as 8 inch, so you can directly read from this bottom chart. You will get C can be taken from this chart, you don't have to interpolate it. So for the new H1 dash, which is 14.2, so this is 12, 13, 14. So somewhere here it is 14.2, and for an E1 by E2 of 50, you can read from this chart so that your value will come around 1.5. So it may come 1 point. So it may come somewhere here. So this value is 1.5. So the conversion factor for the tensile strain can be read from this chart for a dual wheel, which is 1.5, and multiplying it with the one dual wheel or half of the dual wheel, which is PD, will give you the equivalent single wheel load. So this is C value multiplied by 4,500, 6,750 is the equivalent single wheel load. So what approach that we have discussed just now is the tensile strain approach. You are considering that the tensile strain due to a dual wheel is equal to that due to the equivalent single wheel load, and the conversion factors are already available in computing as charts in computing the the tensile strains due to a dual wheel and a dual tandem wheel. So that can be directly used to get the conversion factor C. Okay. Now coming to the next approach wherein you consider equal contact pressure for the single as well as the dual. So whether it is for the single and dual is having an equal contact pressure. So far we have been discussing that the single as well as the dual wheel assembly have the same contact area. Okay, now the assumption is that they have the now the problem is with this method is that it is slightly complicated to solve this solution, Okay. So moving on, the earlier methods that we have discussed based on the equal tensile strain or the equal deflection or equal vertical stress are all based on the assumption that the single wheel as well as the dual wheel both have the same contact radius. Okay, so the contact radius of the single wheel as well as the equivalent single wheel load as well as the contact radius of the dual wheel assembly is the same, is what we have assumed. But in this approach we are going to assume that both of them have the equal contact pressure. Okay, so the radius will be different, the radius will be different, but the pressure due to the single wheel load will be same as that of the pressure exerted due to the dual wheel. The problem with this method is it is computationally difficult. Okay, so let's see, and again the criteria that is used for this approach is the equal interface deflection criteria. So the interface deflection, as we know, is given by Ws is equal to Qa by E into F, where, so in this case I have taken Q as constant, whether it is, so this is a deflection due to Ws is a deflection due to the single wheel and Wd is the deflection due to the dual wheel, and Fs is the deflection factor for the single wheel and deflection factor for the dual wheel is given as Fd. In this, the Q is taken as constant, whereas the area, the radius of contact AS and AD are denoted as AS and AD because they are different. Now equating the deflection due to single and the dual wheel. So QAS by E2 into Fs is equal to QAD by E2 into FD. So we can remove this. So what we know is that ASFS is equal to ADFT. Now what is this AS? It is the radius of the single wheel load. Once we know the single wheel load only, we can get the radius of contact of that, which is root of PS by pi Q, okay, because the pressure is given by P by pi A square, pi AS square. So from which you can get AS, and similarly AD, this is the radius of the dual wheel assembly, is PD by pi Q, root of PD by pi Q. Now, as from the above expressions, we know that PS is equal to FD by FS square into PD, okay. Now, how can you solve this question? Because you have to get the dual wheel factor and the deflection factor for the dual wheel and the deflection factor for the single wheel. But the problem is that for the single wheel, the deflection factor depend upon AS, but this depends upon PS, because if you have to get the radius of contact of the single wheel, you need to know what is the equivalent single wheel load, right? So it is this can be solved only by trial and error. Let's try to solve the same question with an E1 by E2 ratio of 25 based on a equal interface deflection criteria, but with equal contact pressure, okay. So in this question, as you see here, there are two loads, 4500 are the dual wheel loads with a spacing of 13.5 inch, and they have the same contact pressure of 70 pounds per square inch, okay, PSI. And you are asked to find the equivalent single wheel load for a pavement depth of Z is equal to 13.5 inch. And again, since you have a dual wheels, the deflection, this is the equal interface deflection criteria. So the deflections at 3 points are to be noted, and in the case of a dual wheel, and then you have to get the deflection factor, the maximum deflection factor in any of these 3 points, and that factor has to be taken, okay. So this is the interface deflection factors, the figure 2.19 for different E1 by E2. So you have this E1 by E2 is equal to 25. So I have taken that plot here. So PD, that is one of the load, is 4500, for which the load is known to you, so that its radius of contact AD is given by root of PD by pi Q, which is 4.5 inch. So in the case of a dual wheel, the radius of contact is 4.5 inch. Now let us take for the dual wheel, so H1 by AD. Now the Z by A, or the H1 by AD is 3 and E1 by E2 is equal to 25. You can get FD from the figure, okay. So this is E1 by E2 is 25 and this is the H thickness by A. You can note it from here. It's difficult to note from this value from figure 2.19. Now for the dual wheels, you have to note for the different points. So you have considered point number 1, point number 2 and point 3. You can see here 1, 2, 3, and for the left wheel, okay, this is the left wheel and this is the right wheel. So each one of them, as we have already discussed, these are the R by A values, and again for the various R by A values from this chart, okay, various R by A values, and for the given H1 by AD values, you can get the F values. Now, but what about the single wheel load? Because if you have to use this chart, you need this H1 by A value, but A is the radius of the single wheel, which is unknown because it depends upon the, which is not same as that of the dual, right? So which is different, which will depend upon the equivalent single wheel load. But since we don't know the equivalent single wheel load, we don't know the radius as well. So what you do is that you assume a equivalent single wheel load of 8,000 pounds. Since the total load is 9,000 pounds, we assume that the equivalent single wheel load is 8,000 pounds. Now if the load is 8,000 pounds, then its radius of contact is root of PS by pi Q, which is 6.03 inch. Now you can note which is H1 by AS, which is 2.24, and E1 by E2 of 25. You can get the FS value from this chart, okay. So the FS value for the single wheel is noted from the chart as 0.26, whereas for the dual wheel, you summed for the left wheel and the right wheel and you got it as 0.36, 0.36 and 0.36 for all the 3 points. So the deflection values are no same for all the 3 values. So the maximum is 0.36 of course. So FD for the dual wheel assembly is 0.36, and for the Fs for the assumed equivalent single wheel load of 8000 is 0.26. Okay. Now the equivalent single wheel load PS can be computed as FD by Fs square into PD, which you get it as 8630. So you have assumed a value of 8000 pounds, and by trial you determined what is its equivalent single wheel load, and you got it as 8630. Now if you want, you can slightly increase the PS value and again do this iteration and see what is the ESWL. But since you are reading from a chart, you may not be able to get anything at more accuracy may not be possible. So what you can do is that you can take an average value of 8000 and 8630 as the equivalent single wheel load. Okay. So this is a trial and error approach wherein you have assumed that both of the wheel loads have, or the equivalent single wheel load and the dual wheel are having different contact radius, but they are having the same contact pressure. Now this is the last approach which is the based on an equivalent contact radius, not the equal, but it's equivalent contact radius A equivalent, or it is called a ESR, equivalent single axle radial, ESAR. Now what you are going to find is a single wheel load with an equivalent radius that would lead to the same response if loaded by the same total load as the dual wheel assembly. So what you are trying to keep constant here is that the dual wheel load as that of the sum of the two wheel loads, which is, say for in the previous example it is 9000 pounds. So if we load the same 9000 pounds, what is the equivalent radius which will give you the same response? So you are not going to find the equivalent single wheel load, but you are going to find an equivalent radius which will produce the same effect. So A equivalent, now this empirical equation is derived for maximum bending stress due to a dual tire in the interior of a concrete slab as compared to an equivalent radius of A equivalent given by A into 1 plus 0.241 SD by A, where A equivalent is the equivalent tire contact radius and A is the contact radius of each of the given dual tires, and SD is the center to center spacing of the wheels. So this approach can be used for a concrete slab, wherein the usage of this for a flexible pavement is yet to be investigated. Okay. So to summarize, what we have discussed in these two lectures is, what we have discussed so far is, you have a dual wheel assembly, how to convert it into a single equivalent single wheel load. So we have used different criteria such as the same vertical stress or same deflection or same tensile strain with equal contact radius, and the other approach wherein you have considered that the contact radius is different but the contact pressure is same. So likewise you have converted dual wheel assembly to a equivalent single wheel load. Thank you.